Okay, so today we'll be deriving the electric field outside a cylindrical insulator of non-uniform volume charge density. So here in the solid line cylinder, we have the cylindrical insulator with a radius big R and height h. And in this dotted line over here, we have the Gaussian surface, also in the shape of a cylinder with radius small r. So this insulator has non-uniform volume charge density. So typically you'll be given the equation for the volume charge density, and in this case our volume charge density is rho naught times 1 minus little r squared over big R squared. So this right here, this can change depending on the question you get. So I just basically chose this for our question, but I don't know, your professor or teacher can give you any other kind of equation, but to solve it, you'll solve the same way. So what this basically means is that, as your radius increases, as you go this way, as you go out towards the surface of the cylinder, the volume charge density actually decreases. Okay, so we have to solve this using the Gauss's law, which states that epsilon naught times phi is equal to Q enclosed. So epsilon naught times electric flux is equal to Q enclosed. And we can expand this. So epsilon naught times electric flux is electric field times area times the Gaussian surface area is equal to Q enclosed. And we're finding electric field. So we isolate that E. So electric field is equal to Q enclosed over epsilon naught Gaussian surface area. Okay, so first we want to find Q enclosed, the charge enclosed. And to do this, we basically have to take the sum of all the dQs within this insulator, and there's going to be a little bit of calculus involved. So to start off, we can start off with rho. So rho is volume charge density, noted as Q over V, so charge per volume. And because basically the cylinder over here, it's made up of a bunch of small cylinder. Imagine this is like a small cylinder. Ooh. And this is a little bit slightly bigger. Basically a bunch of volumes that make up this cylindrical insulator. And each volume has a different has a different charge enclosed because of this over here. The shape has non-uniform volume charge density. So therefore we can denote Q over V as dQ over dV. Okay. So now dQ is equal to rho dV. But right here, we're given that rho is rho naught times 1 minus little r squared over big R squared. So we're going to replace that. So we have dQ is equal to rho naught times 1 minus little r squared over big R squared dV. Alright, so we have this equation for now. Now what's dV? So we can actually solve for that. So volume of a cylinder is pi r squared h, because that's the base of the cylinder times its height. That gives us its volume. So now we just take the derivative of the volume with respect to r, which is 2 pi rh. So dV is equal to 2 pi rh dr. So now we have these two equations. We're going to basically combine them over here. So we're solving for dQ. So dQ is equal to rho naught times 1 minus little r squared over big R squared times dV, and dV is 2 pi rh dr. Okay, so now we have dQ. Now, to find electric field over here, we obviously need Q enclosed. And the charge Q enclosed, the charge enclosed for this shape is the integral of dQ, so the sum of all the little dQs. And we replace this. dQ is rho naught 1 minus little r squared over big R squared 2 pi RH dr. Alright, so we have this Q enclosed is equal to integral dq, which is equal to integral rho naught 1 minus r squared over r squared 2 pi r h dr. So this integral here, integral dq, because we're finding the electric field outside a cylindrical insulator, basically the dq's only come up to kind of like over here. So this arrow is coming towards you. So the dq's are only coming up to this surface over here. So that's why when you take the integral of the dq's, it's only from 0, the center, to r, which is basically the outside of the cylinder. So you're taking these integrals from 0 to r. So now basically we just solve for this. As you know, you can pull out constants during integration. So your constants are rho naught 2 pi h and integral from 0 to r, and basically you're left with this and this, which are not constants, so you cannot pull them out. And I'm just gonna multiply them right here to make our life easier. So then over here it becomes rho naught 2 pi h integral from 0 to big R of r minus r cubed over r big R squared dr. Okay, now we have this. So now we just integrate this is equal to rho naught 2 pi h. If you integrate this, you get r squared over 2 minus r to the 4th over 4 big R squared, evaluated from 0 to big R. So now we just evaluate this. We plug in big R into here. We get rho naught 2 pi h big R squared over 2 minus r squared over 4, right? Because if you plug this big R here, it becomes r to the 4th, but there's a r squared in the denominator, so it cancels out, becomes r squared. So now we're left with this. I'm just gonna pull out the r squared here. So we're left with rho naught 2 pi h big R squared over 4. Okay, because you plug in this r squared out here, this becomes r squared times 1/2 minus 1/4, which is r squared over 4. Okay, so now you have your Q enclosed is equal to rho naught 2 pi h r squared over 4. Alright, so now we're going to go back to the Gaussian equation, Gauss's law, right here. Electric field is equal to Q enclosed over epsilon naught times the Gaussian surface area. So now I'm just going to rewrite that here. E is equal to Q enclosed over epsilon naught A. And we know that Q enclosed is equal to rho naught 2 pi h big R squared over 4. And then we have to remember this epsilon naught. Now this area over here, that's the area of the surface area of the Gaussian surface. And if we go back to the drawing over here, the area of this dotted line, Gaussian surface, is 2 pi r h, and r is little r in that scenario. So basically it's the circumference of this circumference times the height will give you the area vector, the area of that Gaussian surface. And so it'd be area is 2 pi RH. And R has to be little r here because it's this area over here. This area over here is referring to the Gaussian surface. So now we can simplify a few things here. 2 pi h's cancel out. 2 pi h, 2 pi h, and we are left with rho naught r squared over 4 epsilon naught little r. So basically, our electric field for outside a cylindrical insulator of a non-uniform volume charge density, with the volume charge density being rho naught times 1 minus little r squared over big R squared. So that electric field is equal to rho naught times big R squared over 4 epsilon naught r. So yeah, that was deriving the electric field outside a cylindrical insulator of non-uniform volume charge density. Let's go.